So last time we talked in some detail about the tree reduction step for the ultrametric phylogeny construction algorithm, and I'd just like to very briefly touch upon the equivalent tree reduction step for neighbor joining. It's a little different, mainly because we're no longer constrained by the requirement of the ultrametric phylogeny algorithm that all of our sequences going into its neighbor identification step, all those sequences have to be modern sequences. They have to be contemporaneous, right, under ultrametric phylogeny construction. Whereas with additive distance, we no longer require that. So to make a long story short, the standard tree reduction step that's used for neighbor joining, you could think of it as being like the following. So let's say we have some pair of neighbors, A, B, that we are joining in this step of neighbor joining, and then of course there's a bunch of other tree structure, whatever. So the basic step for tree reduction in neighbor joining is basically we're going to replace A, B by the internal node C that connects them in the neighbor joining tree. So concretely, that means we're going to compute now the distance from this internal node C to all of the other sequences X, Y, Z, etc. In the rest of the tree, basically by subtracting away these distances on the external edges going to A and B. And if you'll recall, we had a slide in last lecture that showed the actual calculations for basically determining the distance for C to any additional sequence. Question? Under the additive distance assumption. Yeah, it's very simple because it's like you're just pruning away the stuff that you just joined, and so the tree kind of gets simpler, and you keep doing the distance calculations, and you just, it's like you're just calculating the edge lengths as you go. Okay, so you're bringing up an important distinction here. So you're now talking about the Q function for picking neighbors. What I'm talking about right now is still just straight evolutionary distances. So imagine you have a matrix of pairwise evolutionary distances. And I'm saying we're going to replace the rows in that matrix that represent A and B with a row C whose distances to other sequences X is going to be computed basically using those simple algebra that I showed in that previous slide. Then you're going to compute Q from those pairwise evolutionary distances, and you're going to take the minimum Q. And strictly speaking, all of the, you only have to update the obviously the U for C because it's brand new. So you have to recompute some Q's based upon the existence now of this UC. So basically, Q for anything with C now has to be calculated anew, if you will. Yeah, so as you say, it's generally negative numbers. That's right. Yeah, that's a good point. Other questions about this? Okay.